think about what happens in thermal analysis compared to other simulation scenarios, like for example, electromagnetics, right? With electromagnetics, we would want to know quite a bit about the materials, or at least what are all the different dielectrics in the vicinity of the system we're simulating. Um, but what you just said about matching up the thermal camera with the simulation data, you didn't mention anything about the material properties of all the different materials that make up the components, for example, which I think is quite interesting. So it sounds to me like there are some things about thermal analysis and simulation in which you're trying to calculate and compare with measurement that are maybe unique to some other simulation scenarios. What would you say to that?
Materials is a good point. We have a lot of parameters in the thermal business, but only one is proportional to the final temperature, and that's power.
Today, we're talking with Johannes Adam, an independent consultant focusing on thermal management. Johannes was recommended to me by another designer I know, and he, of course, is well known in the thermal management community, and he has a very interesting piece of software that does plug into Altium Designer, so I'm very happy to have him here today. Johannes, thank you so much for joining us.
Thank you for having me.
So, you are well known by a few designers out there, and as I said, there's another designer I know who recommended you come and on the show and talk to me today. I'm very interested to learn a bit about your background, and so if you could just go ahead and jump in and tell us about yourself.
I'm not an electric engineer, I'm a physicist. So I'm watching the PCB or the thermal aspects of in PCBs from the perspective of a physicist. Yeah. So I know about differential equations, I know about conservation of energy, thermal energy, and how heat is flowing in the PCB, in the traces, in FR4 and so on, and in the vias, and how the heat is escaping from the PCB, from the heat source to the ambient air, which is very important to know. So I'm in business since about 20 or more than 20 years, learning from scratch, learning from users and other companies. But it's still a very exciting business because the thermal people are in competition with a lot of enemies. Yeah. So a good thermal design maybe is contradicting EMI, production, cost, management, whatever you can think of. So if you start thermal design of a PCB in a later stage of development, you are in a defensive position. Yeah, if the thermal engineer is in the discussion about the layout or the concept of the PCB, then he will be able to contribute more than at the end of the development where everything is fixed. And the only way to modify or to improve the thermal behavior is heat sinks or fans. And then it's obviously too late for most of the applications nowadays. And so that's my business. My software is able to import, so to say, Altium files, do a calculation, give hints what can be done better. You see it in the graphs, and then report back to the electric engineers. The software is not integrated in the sense that you stay in Altium. You have to leave Altium, use my simulator, and then go back. But has the advantage that the thermal engineer can work on its own independently on the designers. He can modify the design a little bit on its own, and yeah, then how to say loosely collaborate with the electric engineers, if this makes sense. It depends.
Yeah,
Sorry, I also have customers or users who don't want to know anything about engineering. They are technologists. They want to select the correct materials, have a rough shape of the traces and then the planes and so on, put some heat sources or traces with current, and go into other sort of details, which maybe an electric engineer doesn't take care of.
I see. I see. Yeah, and you mentioned being in a defensive position when it comes to thermal. I think another way you could even describe it is being in a reactionary position, which is where people are essentially reacting to the thermal problem after it's in a position to totally ruin a product or ruin the user experience, ruin the functionality, however you want to describe it.
Yeah, there are famous examples in the past
Yeah.
where people didn't think, nah, maybe it's also worth to mention extreme situations. So if you have a voltage surge, what happens? Yeah, if the voltage or the current rises from 5 amp to 50 amps for some milliseconds, what happens? Yeah. Or if you have 40 degrees ambient temperature in your pocket. Also. For example, the search stuff is very interesting. I did at least 2 or 3 investigations about that. If you have a search in an inner layer, say 100 milliseconds, this time is too short that the thermal signal is visible or reaches top or bottom so that an infrared camera can detect the effect of the surge. Yeah. So the heat keeps being inside and heats up to 500 degrees or even more, depending on the current. Yeah, and yeah, that's the only way you can detect this behavior or misbehavior.
Obviously, as thermal management has gotten a bit more complex and uh, I guess you could say multimodal, right? There's heat sinks, there's airflow, there's thermal interface materials, these kinds of things. Have the thermal simulation methods and software packages been able to keep up with the way that people manage heat in PCBs or in electronics more generally?
Um, Software is ahead of, of typical thinking about thermal management. So let's talk about thermal interface materials. You take the data sheet, you see a thermal resistance per square inch or so, and then you think, okay, I take a pocket calculator and multiply the power loss times the resistance, and I'm getting the temperature increase. This is it's not wrong, but it's useless because you have to know the amount of heat which is actually reaching the thermal pad. Maybe 50% or even more are diffusing before the heat is reaching the pad, and maybe the components you are interested in is influenced by other components, the heat of other components, which of course bring their temperature to the left and to the right and up and down to the component under investigation. So simulation gives a 3D response of temperature to the heat flux you are creating. Heat and temperature are 2 different aspects of energy. Yeah. You enter the power, the watts, and the results is the temperature, and not the other way around. Yeah. And the temperature is influenced by all sort of parameters like the design, the thickness of the layers, the ambient airflow, other components, other traces, and so on. Simulation will agree almost to 90% what you get with an infrared camera if you know the power of your components and if you know the correct current in the traces of interest. Yeah. And I proved that many times that an infrared image plus minus 5% is a good agreement with the thermal simulation plus minus 5%. That's typical.
It's interesting because I think if you think about what happens in thermal analysis compared to other simulation scenarios, like for example, electromagnetics, right? With electromagnetics, we would want to know quite a bit about the materials, or at least what are all the different dielectrics in the vicinity of the system we're simulating. Um, but what you just said about matching up the thermal camera with the simulation data, you didn't mention anything about the material properties of all the different materials that make up the components, for example, which I think is quite interesting. So it sounds to me like there are some things about thermal analysis and simulation in which you're trying to calculate and compare with measurement that are maybe unique to some other simulation scenarios. What would you say to that?
Materials is a good point. We have a lot of parameters in the thermal business, but only one is proportional to the final temperature, and that's power. Or if you have a high frequency signal analysis, I think the geometric volume you are investigating is very small. It's confined along the trace or between trace and the return. Yeah.
Mm-hmm.
While in thermal we have a wide geometric range of influence. So a central point component is influencing the temperature in the corner, depending on heat spreading in the board. And another component at the corner and one in the center, they will interact, exchanging or accepting or producing shifting power to the other one. So nothing is proportional except more or less the heating power, and that's a function of temperature. That's a function of the circuitry, the function of operation state, and so on. And that's could be complicated if you want to do it in high precision. But typically, if you have an infrared camera and you have a device in front of you, then you measure the voltage and the current and just estimate the power in the component, and that's makes it most accurate.
I think something else that makes this a little different from Ian from electromagnetics, which I don't do thermal simulation. I haven't done it in a long time, so I guess I don't think about this enough. But now that I'm listening to you talk, I'm realizing that in electromagnetics we're often looking at like transients, which can be very fast, or we're looking in the frequency domain. Whereas in thermal, what you're actually measuring on the infrared camera is the static or the steady state.
Yeah.
And so this produces a lot of differences, not just what you do mathematically,
Yeah.
but how you actually understand this proportionality between power and temperature.
Yeah. And the thermal inertia is quite high, so you won't see millisecond spikes or waves in your thermal couples or so. Yeah. So you have to wait. You have to to look at intervals of the order of 10 seconds or so until you see a signature in the thermal couples or in the infrared camera. So that makes it temperature or heat diffusion, smoothes everything down in terms of space and time. Yeah.
Sure, this makes a lot of sense. So you're mentioning here some very interesting facts about thermal simulation, and as I mentioned earlier, uh, you do have a piece of simulation software. So if you could just tell us about your simulation software.
Well, it's a product of our own, myself and some companions or collaborators. We are an independent software producer, so you can run it separately without any electronic design input, just drawing yourself what you want in MS Paint or so, or create rectangles imitating or traces. But of course, the standard use is to import design data from Altium, for example. We are using the low end or the mostly used language, which is Gerber files and drill files, and then combine this to a three-dimensional model. Plus, of course, additional information like um, parameters in Altium, for example. Yeah, if you define your thermal parameters in the design, you can import and other people feed the data into Altium. That's possible. Okay, at the end, the processing is, of course, we are solving the DC electric field in traces, so to say, the current, the voltage field, and the current density distribution in traces and so on. And when you have the current density, you can calculate a local power node by node and use that for the temperature simulation as a input of source of input of heat, together with the components. With or without components, it's up to you. Plus a lot of extra stuff, temperature dependent materials, temperature dependent ambience, temperature, time dependent signals, time dependent in sense of 10 seconds off, 10 seconds off, or 20 seconds off. Supply Excel sheets where you define this mission profile, steady state heating, time dependent transient heating with constant sources and time dependent sources, and a lot of other stuff. But focused on the PCB, no housing, etc., which is maybe unknown to the electric engineer. Then other people are responsible to do the mechanical part.
I see. So when you're defining some of the thermal parameters in Altium, let's say, right? Let's say I have an integrated circuit, right? And I know from some prior testing, maybe with a development board, that I know that when my application's running on, let's say, this processor, that it dissipates a certain amount of power or it heats up to a certain temperature, right? You could account for that in your software.
Yeah, correct.
I see.
Correct.
Okay. So essentially, let's say the integrated circuit heating up to a certain temperature, that would be treated like a boundary condition.
As a source.
As a source, okay.
As a source, yeah. Boundary condition is the air's. Boundary conditions are heat sinks. The major heat sink is the air around the board, and of course, it's possible to specify special parameters for a heat sink, or a screw, or where you think, or a bolt where other people tell you it's permanently 30 degrees, whether it's true or not, but that could be introduced. Yeah.
Sure.
Yeah.
So do you have a demo that you'd like to show us?
Yes, I can show some stuff. Just let me share the screen. So this board is quite well known in the community. It's a 2-layer board with an LED display and then some processors and transistors. So let us assume we know the power of one of those components. One way to bring that power into these data repertoire is to use the parameter manager, which I like most. So the parameter manager, we need the parts, we need the pins. And what you have to define is a column called TRM for the electric part. And the thermal, you can mix both. And we have another parameter called TRM power. That's for historical reasons. Previously, we separated the electrical part and the thermal part, but can be combined as well. So what you just do is you select your component. Have to sort. It's a demo effect.
So I see you have two parts here at the top of this dialog.
I have two parts. S1 has 2 pins, and pin number 2 is, in my definition, is a sink. It accepts -2 amps. Yeah,
I see.
The -2 amps must have a counterpart, a source, where I create the 2 amps, and I choose the component LCD1, pin number 2, 1 amp, and pin number 15, another amp. Yeah, that's the one way to define current. The other way is to do it individually. For example, we know that pin number 12 in U1 has a certain current or voltage value. Define the voltage or the current here, and look for a counterpart, which is the other end of the trace, for example. Yeah. So let's talk about the thermal power. We have another column, thermal power, and here that's the place to define the watts. For example, if we know the wattage of U1, we take, for example, we have 1.5 or 1.0 watts. We know the wattage of U3, 0.5, etc., etc. It's also possible to define an electric resistance of the components and use a component as a bridge between nets. Yeah, and the nets are then linked with an electric resistance of the component, and the current is flowing through the component from one net to the other net. That's also one of the options available. Okay, the user is filling this table, or any other person in the team who knows about the data. So we are then accept changes and close again.
I think you need to click accept changes and then
yes,
execute changes.
Execute changes, I forgot. Yes. The other way is to use the component itself in the schematic and create property. You create a parameter by keyboard called TRM and add the value, which is pin number 2, -2 amps, which is just this one, receiving 2 amps from the 5-volt net from somewhere else, which is the LCD in the other schematic. So here you see plus 2 amps, 1 amp, pin number 2, 5 volt, the other 1 amp, pin number 15, 5 volt net. That's the two alternatives you have here in the Altium environment. Yeah? Okay, when you've done this, you say TRM, click TRM, then a script is launched, and the script is exporting what we need. We need these parameters, we need the Gerber files, the drill files, and the net list, and this is exported by default into a certain folder.
So I can see it's running through several steps here automatically.
Several steps,
script.
Yeah. It's have to wait for the dataset created. Now I'm opening my software. The software is called TRM, Thermal Risk Management. Now we are in version 10. That's a previous test. Let me start with a new. I don't want to save it. So let's say call the model demo, and now I import using the Altium filter. Say define the spatial definition or resolution. And then it's reading and building a 3D model of the board.
So that's where there's a really useful bit of automation is in building that model, because I know in certain simulation modalities, whether it's thermal, CFD, that kind of thing, the model building itself can be quite difficult, and even with CFD uses its own software just for meshing and this kind of thing.
Correct, and meshing is maybe a matter of hours or days if you have a multi-layer board with just 2 layers, and that's quite easy to use. If you work 1 week with the software, you may know 80% of the features, and after years you even learn subtle effects or ways to model more details and so on.
Sure.
But don't be afraid that this Manhattan look of the components, that's intentionally, because we want to see what happens in between the traces, in between the planes. Yeah. So we have a factor of stretching of factor 5 in the vertical direction. Yeah. So we have here the bottom layer, or the bottom plane, and the drilled holes. The red ones are plated, the black ones are non-plated, and there are blue ones for the blind and for the buried and for the back drills and so on. That's a complete set of drilled holes. Yeah, the top layer and the components. This, for example, is U1. U1 has a power of 1 watt. 1 watt we defined just some minutes ago in Altium, yeah, and so on. So what can be done else? So this is the import as you get it from Altium. What you can then modify is the thickness of the layers. You can modify the dielectric materials from a built-in database or your own database of materials. You can add additional stuff here in the level, maybe another sheet, an adhesive sheet on bottom, and then an aluminum plate on bottom with or without fins and so on to have an INS situation, or a plate on a PCB on a heat sink. that's quite flexible. You can do everything. You can delete the bottom layer or replace the bottom layer by just a prepreg to see the influence of heat spreading and so on. Then we have a list of drilled holes. We can parameterize the holes, for example, the plating thickness, 25 microns or not, filled or not filled, filled with a material of your choice. Yeah. And then the most interesting table is what I call the loads table. That's the objects we can modify. And the objects are, it's a long list of stuff. Starts with the components in gray. Yeah, you see all the stuff, even the useless logos and so on. Here we have the 0.5 watts on U3. And if you want to know what did we define, we just use an SQL. So we see here U1, 1 watt, 0.5 watts on the other one. And if we want to make modification, of course, we can modify here. It's not a problem. Let's look at the use. Say U5, U4 also 0.5 watts, and so on. Yeah, it's possible to modify. It's possible to delete. Let us delete the logo. Let us delete this LCD block. Just delete it by keyboard strike. And what about our current? So I'm searching for ampere not equal 0. And here we see the definition in our 5-volt net. We start at, or we are receiving 2 amps on LCD 1, pin 15, pin 2, 5-volt net. And we are extracting my -2 on S1. Of course, in DC, the polarity doesn't matter for the heat calculation. That's just some sort of definition. Let's talk about the net list. The net list is transformed from a network description into an object or body way of description. You see here a colored list of circles or rectangles. For example, the syntax is HP15 is the net name. We have a tilde, and then comes the component or the reference designator, and then the dash, the number of the pin, and that's how it works. Yeah, we have here an object, a circle with net name and component name and parameters. Now what's 5-volt net? 5-volt net maybe is one of those. Let's get this sort of color. This is the 5-volt color, same color in the select, and I see 1 ampere. I can also select this one if I just want to put 1 amp in net LCD _E and so on. I can also identify the position in the graphics and add my values here, and I see it again in the table, and I can modify what I want to modify. If I want to,
right, you could go through and do some experiments here just by adjusting what are the currents in each of the traces and nets.
Correct. And there's a way a quick way to modify. For example, if you want to change the amps for the complete net, say what happens if I multiply the current by a factor of 2, It's just a drop down, add a
Mm-hmm.
new value, and then you have a factor of 2. Yeah.
Yeah.
Now let's calculate to make it short. Environment 20-degree ambient, free convection, and I say start calculation, and it will start with calculating the current density in a trace, yeah, in the trace. Then from the current density, the local heat, and you see here joule heat 3 watts. 3 watts are created in the 5-volt net from position S1 until up to LCD1. And now this local field, power field of the trace is used, and the power of the components is added. And at the end, we end with 106 degree, say 100 degree. Computation is quite fast. It's creating automatic images of the results. So you have a quick look to the results without going to a sequence of post-processing, which is also possible. But typically, you are watching this sort of images. You see in red a very thin part of the trace, and 2 amps is obviously too much or we have 4 amps in total. It's too much for this trace. This is the top layer, and here are drilled holes, here are PDHs, and this is the bottom layer situation.
Yeah.
Here you see components act as a heat sink. So
Mm-hmm.
the cold components extract heat from the trace, and locally we have a lower trace temperature than where no components are. That's very funny.
Yeah, that makes perfect sense.
Yeah. Voltage drop. This is a voltage of minus 0.4 amps. Here we have a plus 4 amps, so total voltage drop is around 0.95 volt. Sorry, minus 0.4 volt and plus 0.54 volt, and so on. You can also gauge the current, the electric parameters with 0 volt or etc., so that you have a voltage gauge situation.
I see. So that didn't take very long. I mean, compared to like a full, 3D tool like ANSYS, for example, right? Let's say you were to do this in ANSYS, it would probably take much longer.
Yeah.
And then also, we care about what's happening at the surface of the PCB, but I think the ANSYS temperature field is going to give you these, gradients through the air above the PCB, which are probably not so important in a lot of situations.
Yes, of course. Yeah. ANSYS is interesting for mechanical calculations when you have a housing, have a fan, inflow, outflow, and so on. But that's maybe not known very well to the electronic designer. He is trying to simulate the laboratory situation without stuff he doesn't know about.
Well, and I think there's a good place for this kind of tool because it lets you quickly identify before you even go and build something. Hey, maybe we need a heat sink here, or maybe we should try a fan, or maybe we should try to, use a thermal interface material to
Yeah.
bond to the enclosure, something like this. I think very informative demo and very good to see, that static thermal calculations definitely have a place in electronics design, and you don't have to go for the full 3D simulator as the first tool. It's probably the tool that you need when you're starting to maybe design a more elaborate thermal management strategy, maybe something that involves fluid flow. And like you said, it's more useful on the mechanical perspective than it is from the electrical perspective.
Yeah.
Okay. So where can users go to learn about your software and possibly get access?
Yeah, just visit my website. It's www.adam-research.com. There you see a lot of papers and introductional stuff, test cases, white papers, comparison, and a button. Oh, I want to have a test installation, a trial installation, which is, of course, it's not a problem.
Okay. Well, to anyone that's interested out there, make sure to check out the link in the description if you're watching on YouTube, and you'll be able to get directed over to the website. Johannes,
I
sorry,
forgot
go
to
ahead.
mention there's also a YouTube
Yeah.
channel.
Oh, yes.
Yeah, and with examples and theory and how to do.
Excellent. Yes. We'll also link to that in the video description here. Johannes, thank you so much for joining the podcast today. This was very informative, and I hope that all of our listeners will go and check out your software.
Thank you for having me, and thank you.
To everyone that's out there listening, we've been talking with Johannes Adam, independent consultant focusing on thermal management. Thanks, everybody.